Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're going to take a closer look at futures of transformer. So let's dive right into it. Now first thing you have to understand, what is the problem with our current transformer infrastructure. Now first, they are inefficient. Now as I already specified in my last video about transformers, is like even though they are, let's say, 98% efficient, that's more than good enough for your home application. However, when you are talking about substation scale transformer, that 2% can translate up to 2 megawatts of loss, or sometimes even 200 megawatts of loss in case of some really big transformer. So that is a lot of energy that transformer has to dissipate, and not to mention that is also lost revenue. So there is a reason why we want a transformer that is almost 100% efficient. It's not a it would be nice to have. No, it has to, we have to have it, because that heat is very dangerous to neglect. And not to mention your lifespan of transformer and the oil that are used into it, that also degrade if there is a lot of heat around involved. So, and on top of that, let's say you built a transformer, everything fine and dandy, but they are huge. Like this is a person, and these are small transformer. There are transformers that are so big that even if you see a photo, it will not make sense to you unless you stand next to it. Then you're like, okay, this is the size of a building. Like, transformers are very big. So before we go into further into detail about how we're gonna make a better transformer, you have to understand there are something that we call types. Basically, there are two general type. Is what we have core type. Basically, the winding is on the both ends. This is three phase. This is three phase. Now there is shell type. Now shell types are actually more efficient, and they are also what we call more short circuit resilient. Basically, if there is a spike current, these can handle it and dissipate it much more effectively. So these are better transformer. However, this is cheaper transformer. So this is why almost all transformer that you will see in your pole mounted substation or things of that nature would be generally what we call core type. Basically, it will have bare minimum that it needs to have. Then you're gonna have shell type in very high application, very expensive transformer, which generally is needed when you are talking about hundreds of megawatt being transmitted. So in those sort of scenario, people generally try to use shell type. But be aware, because it requires more material, it is inherently more expensive. So as you can see, these things become quite big and complex. So these are the type. Now in future, as in right now, we are going to 3D. So basically the benefit of 3D is best of both worlds. As you can see, these are the core architecture that I'm showing you. As you can see, this only has same material count as a shell type, as in core type, but has the benefit of shell type because each coil is coupled to another. So magnetic field is very equally distributed. And in case of three-phase transformer, this also has the advantage that if one phase goes out of sync, let's say one phase is suffering too much loss or too much basically power draw, it can manage it out, it can balance it out, and it does not require ludicrously more component like for shell type, because you have to basically lock it inside. So this is best of both worlds. You get material consumption of core type, and you get the power efficiency of shell type. So that is why we want to go to 3D future. Now you can search for this as 3D T-shaped transformer, hex transformer, things of that nature. So this is, we make three coils, put them into a triangle, and then put windings on top. And you can see any transformer that you see, especially new ones, if they are triangle in shape, generally they have this sort of structure inside it. So then the question becomes, how the heck we're gonna wind it? Now you have to understand, the core cannot be a one big thick block, simply because it will be very, very inefficient due to what we call eddy current. So generally what we do is we create laminates. So things of this nature, basically you have sheet on top of sheet on top of sheet on top of sheet. Now that is not only tedious, it's also inefficient. Now this is better than a big hunking block, but it is not as good as we can make it. However, when you are talking about this sort of core transformers, we generally wind it up. Now this is one continuous spool, so that's the benefit aspect of it. It's very efficient, and not to mention but of course the side effect is you have to have the machine. Basically, I have provided the link down below. Here you can see the video how these things are made. You have to have the machine, you cannot do this by hand. But once you do it, you will have basically a core that is far more precision built and has higher efficiency, simply because there is no more break every few places. So this is how we build the core aspect of it, as in the sides of it, the basically magnetic flux management devices, and they are generally angled in such a way that you can put three of them very close to each other without any space loss. So it gives very, very good transmission in terms of magnetic energy. So that's how we make the core, and it's each core is basically one long strip like that's it, one long strip. You don't have like, okay, I'm gonna cut it for top, I'm gonna cut it for side, and then I'm gonna lay it on top of each other. It's not like that. It's just one large spool. So this is how we take care of the core aspect, as in the core. Then comes the fact how you're gonna wind it. It's very complex. If you have core, generally what we do in winding, we make the winding and we slide it into the transformer. In this, we don't do that. We can't do that because it's internally locked. You can't go inside it. So what people came up with is that they bolt a pipe on top of it, and that pipe is being rotated by a gear, and you just basically tie on something and then you start spooling. And I have provided the video of this also, and this also makes it very quick, efficient, and also allows you to have very high quality windings. And you can see like there are many automation grades of automation. Some are like you have to have one person like doing spooling properly. Some scenarios there are like person there just to watch it. So there are varying degree of automation depending on how much money you are willing to spend. So this takes care of the winding aspect of it. So you have one thing that is continuous, then the winding is also continuous, so it gives a very, very high efficiency. Each of those little things add up into higher efficiency. So that's how we take care of winding, and I would urge you to watch the video that are showing down below, because it's kind of crazy once you actually see these machines in work, like while they are working. So it's kind of amazing. Then the question becomes, why the hell bother with this many things? We have a transformers architecture and it does work. It has been working for 100 years. Why the heck change it? Now, first thing you have to understand, this new transformer that I'm showing you, basically the T-type transformer, it does requires very few human labor. So if power consumption goes up in a city or in a block, every transformer has to come from somewhere. If it takes like let's say 10 people to make transformer, now it will take only 2 people to make that transformer. So we can supply a larger audience. Basically you can take care of India or China. So in those sort of scenario, reduced labor basically also reduces cost and also increases the production. So that is first aspect. Second, because it is far more resilient to short circuit. Once you have short circuit in any single phase or in all 3 phases, it can endure it much more effectively without getting self-destructed. So for that reason, we really want this. Like this is a safety issue. Now, when I say short circuit resistant, does not mean like you can't do any short circuit that will destroy it. It's just that normal transformer will give up before this. So that's the core aspect. It's like, okay, your transformer, let's say it can handle 10 short circuit events. This can handle 12 to 30. So those actually adds up, like especially when you're talking about in terms of a country where there could be hundreds and thousands of transformers. So even if you are adding extra life by let's say 15 or 20%, it translates to a lot of money. And on top of that is 30% lighter. So that inherently means if you are mounting it on pole, A, it will be much easier to mount. B, if you are mounting at the same equipment that you had for older transformer, you can mount a higher capacity. Basically the kVA rating, you can be sure that you can easily, safely put a much bigger transformer in terms of kVA rating, not physical weight, because it is 30%. So either you can put, okay, it's just lighter, 30% lighter, or you can put, okay, 30% more capacity. So it gives you a lot of flexibility with that and higher efficiency. Now, when I say higher efficiency, do not think like, okay, normal transformer is let's say 98% and this is like 100%. It's not like that. It's just 1% more. Now, if you are looking in terms of like a whole country, that 1% adds up into a lot of energy. So that is the reason why people are doing this. And on top of that, with modern advancement in manufacturing, because people had this idea like to make a core transformer, but it was ludicrously expensive and could not even be dreamt of. Now with like spooling technology, basically we are making a continuous spool, then basically refining winding technology where we can wind it automatically. All those things led to this technology. This is not something that you will see, oh, tomorrow every transformer will be replaced with. This would be like 10 transformer has been replaced with new one of them would be this. Then the next time the transformer, 5 of them will be this. This will be slowly replacing everything that you see around it. However, there are certain limitations with this, specifically when you are talking about ludicrously huge one. The biggest one I could find is only 5 megawatt, and substation transformer can go upwards of 300 to 12,000 megawatts. So I don't think anybody has yet manufactured any transformer that is big enough for those scale. However, this will easily, you can find in a wall mounted substation near you. So there's a lot of potential in this kind of transformer, simply because A, it's very easy to make, B, it's more efficient, and C, it's lighter. So all those things combined, it actually has a lot of scope for growth in the future. That is why we want to do with this. That is why we want to change something that has been going for 100 years, because this is inherently better. So this was my presentation on T-type transformers. I hope you liked it or learned from it. In that case, please leave a like, click the ads that are shown in this video, that will directly help me. If you didn't like it, don't worry about it, you can press dislike. I would urge you to press it twice, and you can also leave a comment because I reply to all of them, and subscribe, press the bell icon if you are free, and as always, thanks for watching.